Okay, lecture 3. We'll see now how to generate a memory address. Okay, there is a logical and physical memory address. Two ways of representing an address. The logical address is described as such. The address in some memory segment, you store the beginning address of the segment inside one of the registers, and then you add an offset. Okay, how many memory locations you have to move up to get to the required memory location to get the physical address. This offset is usually stored in registers, pointer registers, index registers, base registers, or the instruction pointer. All right, both the segment register and the offset register are 16-bit registers. All right, an example of writing a logical address would be as such. You give the value inside the segment register, then a colon, then the value of your offset. Okay, two 16-bit registers. One segment registers, and the other one could be a base register, an instruction pointer, or whatever, index register, or just a pointer register. Okay, for example here, this is a logical address pointing to a memory location inside your code memory segment. The beginning address of your code memory segment is stored in CS. Then you move up these many locations in hexadecimal, 100 hexadecimal, to get to the required memory location inside your code memory segment. Okay, the physical address is a 20-bit long, all right, but the registers used to refer to this address are all 16-bit registers. So what you do to get the physical address, all right, composed of 20 bits, you get the value inside your segment register multiplied by 10. We previously mentioned this. You have to add 4 binary zeros, or equivalently, a 0 hexadecimal digit should be placed in the least significant bit, which is equivalently, you take the value inside your segment register, multiplies it by 10, then you add the offset to it. This will get you the physical address of some memory location. For example, if a segment register contains this hexadecimal number and an offset register contains this hexadecimal number, to get the physical address, you take the value inside your segment registers, multiplies it by 10, add this to it. It gives you the 20 bits representing your physical address. The 20-bit physical address. Okay, for example, given these values inside your code segment register, data segment register, stack segment register, and the extra segment register, the 4 segment registers, and bx also is given. As you know, bx goes only with the data memory segment. So you have to get to the physical address should be represented by multiplying ds by 10, add the 200 hexadecimal to it. So your physical address is ds and not any other segment registers. ds, the data segment register, multiplies by 10, add bx to it. This gets you the 20-bit physical address. Okay. Okay, the flag register. Now we're talking about the flag register. It is named the flag register by Intel's people, while Motorola's people used to call it the status register, because as a matter of fact, this flag register is composed of some bits which reflects the status inside your ALU, whether the number you're dealing with are negative, positive, a zero is generated, and the like. All right. We have here 9 bits for the flag register, and as we mentioned, they reflect the status inside your ALU. If you are doing some arithmetic or logical instructions, the value resulted is indicated by the flag register. And we have 9 flags, 9 bits, stored in a 16-bit flag register. So we use 9, and the rest of this register, the other 6 bits, are never used or referred to. They are divided into two groups. A group of 6 bits, they are named CF for carry flag, BF for parity flag, AF for auxiliary flag, zero flag, sign flag, and the overload flag, O for overflow flag. And the 3 other bits are trap flag bit, interrupt flag bit, and direction flag bit. What each of these bits refers to will be shown shortly. So these are the positions of the 9 flag bits inside the 16-bit flag register. The function of these flags are as such. The carry flag bit, if you're adding numbers or subtracting numbers and a carry is generated or a borrow is needed, the CF flag bit is set whenever a carry is generated or a borrow is needed. And it's reset if no carry is generated and no borrow was needed. Okay, the parity flag bit, if the result contains an even number of ones, the parity flag bit is set. If it contains odd number of ones, the parity flag bit is reset. Okay, the auxiliary flag bit, if you're adding numbers at the fourth bit, the bit between two nibbles, if you're adding or subtracting numbers and midway a borrow is generated or a carry is generated or a borrow is needed, this auxiliary flag bit is set whenever a carry is generated or a borrow is needed when you add two numbers midway between the two numbers, so at the fourth bit. And AF is reset if no carry was generated and no borrow was needed. The zero flag bit, if the result, if your arithmetic or logical operation is zero, this zero flag bit is set. Otherwise, it is reset. The sign flag bit, if the number generated out of an arithmetic operation was negative, the sign flag bit is set. If it was positive, it is reset. All right. The function of these flags. The trap, the rest, the other group, the trap flag. The trap flag bit, you set this trap flag bit, you put it a 1 whenever you need to make your processor goes step by step, execute an instruction, waits for you to make it proceed to the next instruction. This is good when you are debugging a code. If you are debugging a code looking for an error, it's better for you to do an instruction by instruction. You let your processor execute an instruction, you check your registers, you check your memory location. If everything is okay for you, you go to the next instruction till you find your error and correct it. So you set your trap flag bit to go to the single step mode, you reset it, and you go normally. Automatically, your processor will execute your code and instruction by an instruction without stopping between the two instructions. The interrupt flag bit, if you are trying to interrupt your code, you set your IF to 1 for a maskable interrupt. Once you're done with your interrupt, you reset it to go to the normal operation. Overflow direction flag bit. The direction flag bit, if you are reading an array and you have a choice to go forward or reverse. If the F is set, it means you will automatically decrement your address. You go backward. If it's reset 0, you go forward. You increment automatically your address. The overflow flag, if the result out of some operation cannot be fit inside your register or memory locations, this overflow flag bit will be set, indicating that the result is larger than the place prepared to be stored in. It's reset if things go normally. Okay. And sending data to the computer or getting a data from a computer, all data are zeros and ones. So you have to have some format to know what these data represent actually. Okay, so we have an ASCII format, a binary coded decimal format, these 8-bit signed and unsigned integers, 16-bit signed and unsigned integers, 32-bit signed and unsigned integer, and short and long real numbers. So these are different formats to represent your data with. Okay, let's talk first about the ASCII data. In dealing with computers and keyboards, you have to send and receive alphanumeric characters, the alphabets A through Z, lowercase and uppercase, and the rest of the characters, the plus, minus, equal, ampersand, and the like. So you have to code these alphanumeric and non-alphanumeric characters for your computer and your system to be able to represent a text, for example, a graph, for example, and whatever. So what you do, we have 26 alphanumeric characters, 26 uppercase, 26 lowercase, that will add up to 52, and the rest of your non-alphanumeric character, the equal sign, the plus, the minus, the percent sign, and the like. So you would have maybe less than 100 characters, 100, 101, 102. So 7 bits would be enough to represent your code. And some systems, they add an 8th bit to check whether the data read or written is correct. They add an 8th bit for the parity. So if the number of ones in your byte is an even number, you place a 0 inside these 8 bits. If it's an odd number, you place a 1 if you're dealing with an even parity. In some printer systems, this 8th bit is used to differentiate between text, alphanumeric character, or graphs. If you're trying to print out a text or a graphics characters. All right, here is the table for the ASCII code. For example, uppercase A is represented by 7 binary numbers. Okay, you can get them from the 41 hexadecimal, the 41, all right. So the 41, you have a 1, 0, 0 for the 4, and for the 1, you have 0, 0, 0, 1. So these are the 7 bits representing the uppercase A. The lowercase a is represented by 61, and the decimal digits from 0 to 9 are represented by the ASCII. In an ASCII format, the hexadecimal digits from 30 to 39. Okay. Okay, the second type of format is the binary coded decimal. So you code the decimal digits into binary, and you need 4 bits to do this. To code the decimal digits from 0 to 9, you need 4 bits starting from 4 zeros ending with 1001. Alright, and when you store the binary coded decimal digits, each digit is composed of 4 bits. So you can store 2 binary coded decimal digits in a memory location which is a byte wide. If you do so, we call this a packed binary coded decimal storage. If you choose to store only 4 bits in a memory byte, we call this unpacked binary coded decimal storage. So you can store 2 binary coded decimal digits in a byte or 1, depending on the available memory space you have in your system. Okay, the third type of formatting is the byte format. You store your numbers into bytes. Alright, if you're dealing with numbers that can be stored easily only in 8 bits, your range of numbers can be stored in 8 bits. You use the byte format, unsigned byte format. So if you don't care about the sign, you need to deal with the absolute values of numbers. No sign is needed. Use the 8 bits, to store your number. And here is the weight of each bit. This is the weight of the least significant, next least, and the most significant. So if you place here a 1, so you have 128 as a number with you. If you store in a 0, you don't have any. If you store a number 1, you have your 16 weight with you. If you care about the sign, use a byte format. Okay, here the least number you can store is a 0. When you place 8 zeros, and when you place 8 ones, you add up 2. Here is 1 plus 2 plus 4 plus 8 plus. You add these weights, you will get 255. So the unsigned number range from 0 to 255. So if you're dealing with numbers inside this range, you'd better use the byte format. If you care about the sign, the most significant bit is used for the sign. 1 if your number is negative, 0 if it's a positive. And here are the weights. So the least number you can store is when you place a 1 here and zeros here, you will get minus 128 as the lowest number you can store in, which is negative. Otherwise, if you have a 0 here and you add up these weights, you will get 127. So the range of the signed number is from minus 128 to 127. From minus 128 to 127. Okay. And negative numbers are usually represented by 2's complement. By doing so, we can use adders to subtract numbers, because negative numbers, when represented by 2's complement, you can add them to numbers, and then you get the uncomplemented result for the final result. For example, the value 81, this is a byte format. You have 4 bits, hexadecimal, 4 bits. If you store this number as unsigned, you will get the equivalent of 81 hexadecimal would be 129 in a decimal. Okay, so the decimal equivalent of the 81 hexadecimal would be 128 if this is to be treated as unsigned. But if you treat it as signed, as signed, you will get the weight of the most significant bit, which is this is 1 0 0 0, and then 3 zeros and 1. So you have the weight 1 and the weight minus 128, so you will get minus 127. So 81, the same hexadecimal number, if it's been read as unsigned number, it gives you 128 for its decimal equivalent, or minus 127 for its decimal equivalent if it's to be treated as an unsigned. Okay, if your range of number increases, you may use 2 bytes or a word to store your number in. If you do so, here are the 16 bits for the unsigned numbers, and here are the weights of each bit, and here are the weights of each bit. We use the word format to represent or to store signed number in. Usually the most significant bit is negative, and when you place a 1 here, you make sure that your number would be negative. Okay, to store the word, so each number needs 2 bytes to be stored in. So there are 2 different methods you can do this, because bytes in your memory is assigned addresses. So you have 2 bytes. Do you place the high byte or the low byte, the least significant byte? Do you store it in the lower address byte or the higher address byte? You can store your lower byte onto lower address byte and the higher byte into your higher address byte, and we call this the little Indian format. All right. Okay. So most in high, least in low. So this is the little Indian format. For example, if you have this number to be stored at this address, so you have to point to 2 memory locations. This is the address of the first or the lower address byte, and this is the address of the higher address byte. If you take low byte into the lower address and the high byte into the higher address, this is the little Indian format. All right, 1234. If you do the opposite, it's the big Indian format. You take the low byte into the higher address memory location and the high byte into the lower address memory location. We call this a big Indian format. So you can, if you're dealing with a higher range of numbers, you may use double word, 4 bytes. Example, this is a 4 byte. This is 1, 2, 3, and 4. We need to store this number at this address. So if you have this address, you have to go up 3 more locations because you need 4 bytes to store the number in. Okay, so you go, this is the given address, you add 1, another 1, and another 1. So you have 4 memory locations to store your number in. Again, low byte into the lower address memory location. This is the little Indian format. Okay, 78, 56, 34, and 12. This is how to store double word in memory following the little Indian format, low in low and high in high. The little Indian format. The double word. Okay, we need sometimes the double word format. Okay, to store addresses in. The value inside your segment register and the offset. Each of them needs a word, a 2 byte to store it in. If such an address is to be stored here, again you would have 4 memory locations. So you add 1, another 1, and another 1. All right, you take the offset 5623, then the register 0010. So the most significant in the highest and the least significant and the lowest address byte. Low in low and high in high, which is the little Indian format. Real numbers. How to store and deal with real numbers. Real numbers or floating point number is looked at as a mantissa, which is the fraction of this real number, and an exponent. Okay, so this is the number represented as a real number. You need the exponent to raise the base to 2, then the fraction to be added to this to get you the whole real number. For example, if you have a decimal 12, which is equivalent to 1100 binary, how would you represent this in a floating point format? This number can be written as 1.1 times 10 to the 3. 10 to the 3, so you have to move this binary point 3 locations to the right. 1, 2, 3, so you have 1, 1, and this is the second and third locations, so you get back to this. So this is the way you represent this number into the real number format. So we have here a mantissa of 1 and an exponent of 3. You give only the mantissa and the exponent. So the mantissa is 1 and the exponent is 3. All right. So we have a short format and long format for real numbers. The short format is composed of 4 bytes. 4 bytes, the first byte, we take the most significant bit, we reserve it for the sign. Then we take 1 byte, 8 bits for the exponent, and the rest for the mantissa. And we call this 8-bit excess 127 exponent, because the exponent would be represented by the number plus 127. All right, so we have 23 for mantissa and 8 bits for 23 for mantissa, 8 bits for the exponent, and 1 bit for the sign. The long for, you have 8 bytes. So again, the most significant bit is reserved for the sign. Then you have a portion of these 8 bytes for the exponent, okay, and the rest for the mantissa. The exponent is 11 bit, the mantissa is 52 bit. All right, and again, to determine the exponent, you have to add 11 ones, which is 1023, to your real exponent. For example, here, you have 12 decimal. Its binary equivalent is this. Its normalized is this. 1.1, 2 to the 3. The mantissa is 1. You have 23 bits for the mantissa. You place only a 1 and the rest are zeros. Regarding the exponent, you have 3, which is represented by binary as this. All right. 1, 2, 3, 4, 5, 6, and 7. It's in excess 127, so you have to add 127 to this to get the number to be stored in your format. So 1 plus 1 is 0 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 0 and carry 1. 0 and carry 1. 0 and carry 1. 0 and carry 1. 0, 0 and 1. So this is 0, 1, 0, 0, 1, 0, 0, 1. So this is what you place here. Okay. All right. 0, 1. Then 5 zeros and 1. Okay. And you can exercise with the rest of this table to make sure that you comprehend how numbers are represented in computers as real numbers, what is the exponent, and what is the mantissa. This is the end of lecture 3. We'll see you in lecture 4.